Hi. So here we're doing permutations with identical objects. So what happens to a permutation when we have objects that are the same? Okay. So far we've just been looking at objects where we have all different arrangements. But something happens when we have objects that have the same features. So we're going to explore how many different ways letters can be arranged if some letters are identical. List the arrangements of the word O with one uppercase O and one lowercase o. Well, we could go O-O-H as in the original. We could switch those two O's, have a lowercase and an uppercase. Okay. Now we could move the H over, so we could go O-ho, starting with the uppercase, or we could start with the lowercase. Okay. We could again move the H over, uppercase, lowercase, and then we could flip those two. So we get a total of 6. Now, how could we numerically account for that? Well, our first option, we have 3 choices, times the second option, we have 2 choices, then times the third choice, which is only one remaining option, which gives us a 6. Okay, because this equals 3 factorial. Okay. Now, what happens when we have O-O-H and they're both uppercase? Well, this changes the number of arrangements. So we can start with our O to begin with. Then we might change the H to the middle. And then we might change the H to the front. And that's basically all the ways we can arrange them. Now, how could we calculate that numerically? Well, we're challenged a bit because we don't really have 3 choices in the beginning. We only have 2, an O or an H, but there are 3 different things that we can put there. So we're challenged when we're asked to numerically calculate it because of those having two O's. So it's really difficult to numerically calculate those arrangements. However, we can map that out. It's small enough that we can map that out. Now, there is a method to doing it when there's duplicated letters, and we're going to see in the next one. So how can we have numerically calculated that? It blows my mind. Okay, I don't really have a solution for you in terms of, our factorial. So let's look at the next one to kind of show what we can do. What if we had O-O-O-O-H, 4 O's, all in uppercase? Let's think about our arrangements. First, we would have this one. Then we can move the H over. Then we could move the H over again. Then we could move the H over again. And then we could move the H over again. So I have 5. Now, here is, because there's 5 letters, right? But only one of them is the H. Here is how we come to our solution numerically. When we have when we have identical objects, what we do is we think how many objects we have, and that will be 5 factorial. And then what we have to do is we have to say how many are duplicates. Well, in this case, we have 4 identical objects. So what we do is we put that underneath. So in order to get the number of solutions, we take 5 factorial and we divide that by 4 factorial. So 5 factorial is 120. 4 factorial is 24, which equals 5. Okay, now if we go up to the previous question, we had 3 objects. We have 2 identical. When we divide that, 3 factorial is 6. And 2 factorial is 2, which gives us the answer 3. So basically what's on top is number of objects. And then below is the number of identical objects. Okay, so let's see how that works. When arranging objects, some of the items are identical. Some arrangements become repeats. Okay, so when we have identical objects, we're going to get repeats in the arrangements. So the number of permutations of n objects where A objects are identical and perhaps another B objects are identical or C objects are identical and so on, this is the formula we use. So we can use it for having multiple identical objects. Okay, so and we'll look at different situations for that. So let's look at this one. In how many ways can all the letters of the word Canada be arranged? Well, let's see. We have 6 letters and 3 are identical. So, we could list out a whole bunch of different arrangements. That might take a while, but we can use this formula. And we can go 6 factorial over 3 factorial. And basically what we're doing is we are dividing out the repetition. Okay, so 6 factorial. So 6, math, PRB, 4 is 720, divided by 3 factorial, which is 6. 720 divided by 6 equals 120. So that's how many different ways the letters in the word Canada can be arranged. And that takes into consideration the fact that we have 3 identical A's, right? Okay, so because that means that, it doesn't matter which of those A's it is, they can be in different arrangements, they still look like the same permutation. Okay. Arranging wins and losses with restrictions. So let's take a look at how that works. In order to make the playoffs, a basketball team must win exactly 5 out of the next 9 games. So they need to win 5 of the next 9 games. Okay? Assume they lose the other 4 games. How many different ways can this happen? So maybe they win the first one, lose the second one, win, lose, right? Or maybe they win the first 4, lose the next 4, and then win the 9th. Okay? So we're assuming that they have 5 wins. 5 wins and 4 losses. So W, 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 and then 1, 2, 3, 4 losses. Okay, so we have 9 choices, and we have 5 of them are W and 4 are losses. So we have 5 repeats of one and 4 of the other. So using our formula, it's going to be 9 factorial divided by 5 factorial times 4 factorial. And you can put that whole thing in your calculator, or you can figure out what each of them are equivalent to. If I put that all in my calculator, I'm going to do it in pieces because then it's easier to check if you're getting it right. So 9 factorial is 3, 6, 2, 8, 80 divided by, 5 factorial is 120 and 4 factorial is 24. So if I divide that, I'm going to get 126. So there's 126 different ways they could win and lose win those 5 and lose those 4 games over the next 9 games. Okay? Now, suppose the team wins game 9. Then how many orders are possible for the team's results? Well, we know 1 is definite. So what we have to, that means that we're just looking at the 4 wins and the 4 losses before that 9th game, right? So here we have 8 games with 4 wins and 4 losses. So for that one, it would be 8 factorial over 4 factorial times 4 factorial. So for this option, 8 factorial is going to give us 40,320 all over 24 times 24. And when we multiply that through, we'll get 70. So there's 70 different ways if we assume they have to go to the 9th game for their last win. Now, suppose the team loses exactly the first 2 games, then how many other orders are possible? So we take out those first 2 wins, right? Because we know them. We're knowing them. And then we have 3 wins and 4 losses. And there's 7 games, okay? So we'll have 7 factorial over 3 factorial times 4 factorial. And we'll get from that we will get, let's see, 7 factorial, math, for 5040 on the bottom. 3 times 2 is 6. And then 4 factorial is 24. So we would get 35. Okay? That would be the possible orders for the next 7 games. Okay? Oh, wait. I read it wrong. They lose the first 2. I'm sitting there looking at it going, what? Never mind. I've got to redo this, right? Ignore. They lose. I read wins. So let's fix that. So what did they really do? Okay. They had a loss and a loss for the first 2, right? And then that means then they have their 5 wins, and then they have 2 other losses, but we're only concerned with the 7 games at the end. So 7 factorial over 5 factorial times 2 factorial. I am so sorry. I read that word as wins, and that would be incorrect. Okay? So when I multiply through that, for my 7 factorial, I got 5040. 5 factorial is 120, and 2 factorial is just 2. So I multiply that through and I get 21. Okay, my apologies. Alrighty, let's take a look at some other options. So obviously when we have a list of things, it's good to kind of map out what they are, circle the things that are identical or draw them in a certain color. That helps. I like colors. And just kind of figure it out in that way, okay? And always look at what the restrictions are first, okay? We have another method here, solving a permutation involving pathways. So let's look at these. These come up. Julie's home is 3 blocks north and 5 blocks west of her school. How many routes can Julie take from home to school if she always travels either south or east? Solve in 2 different ways. So, looking at our map, just that's north, that's south, that's west, and that's east. So she has 5 options going east, and she has 3 options going south. So, and I'm going to put it actually south in a different color. So she has 3 there, and she has 5 here. Okay. So she can go, looking at this, she can go east, 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 but she can go it on different pathways. And she can go south, south, south. Okay? No matter how many she takes, it's going to take her this many steps to get there, right? So if she chooses to go, so if we take a look at this, if she chooses to go, I'm going to go east and then south and then east. I'm going to put it on a brighter color, east and then south. And then maybe I'll go 2 over this way and then this way and this way, this way and home. She still, no matter what path she takes through this, she's going to have to take 5 east and 3 south, because she's never going backwards. She's never going north or west. Okay? So it doesn't matter. She's always got 5 choices of east and 3 of south. So when we do that, we take into consideration the total number. So she has 8 moves. Okay? 5 are east and 3 south. So we put that in our calculation, 8 factorials on the top. We divide by 5 factorial and 3 factorial. And when we put that through and we multiply, you're going to get 56. I'll trust you guys to do the calculator work. Okay? The big thing is figuring out the pathways. And because we're limited on the direction we can go, we can kind of settle it down that way. Now, Julie has to work after school, but first she has to stop at the bank. Traveling only east or south, how many routes can she take? And in the one before, it said solve in 2 different ways. I like our factorial way. Yeah, okay, we're going to do it that way. So here she's got 2 different journeys that she takes. So she has to do both. So it's school to bank and then bank to work. So it's an and, it's not an or. And remember we talked about and being multiplying. So we have to figure out the top part and then the bottom part, and we're going to multiply them. So let's take a look. For school, she goes 2 east and 2 south. So there's 4 moves in total. So school to bank. She has 4 moves, 2 east and 2 south. Okay, so that would be 4 factorial over 2 factorial times 2 factorial. Then she has, and she's got bank to work. And that goes 2 east and 3 south. So she's got 5 moves. And it's 2 east and 3 south. So what you see is that she has 2 different journeys, but what we have to do is calculate each of them separately, and then we're going to multiply them. Okay? And that's going to help us kind of figure out exactly what's going on in that journey. Okay, so let's figure that out. So from here, it'll be 5 on the top, 2 factorial, 3 factorial. And it's an and, so we multiply. If it was she could do this or that, we would add, right? Remember we said or is a adding and is a multiplying. So if you figure out 4 factorial over 2 factorial times 2 factorial, you should get 6. And then 5 factorial over 2 factorial, 3 factorial, you should get 10. So she has 60 different roots. And that is how that is going to work. Okay? Right. Alrighty. Let's look at another example. So I'm going to scroll up here and read through the next question. So example number 4. It's again a pathways question. Julian is planning a trip from Calgary to Denver. The map below shows the different flight options from a particular airline. I don't know what airline he's flying on, but he has these different pathways that he can go through. Now, so what it means is that he's going from Calgary to Denver. So he can either fly straight from Calgary to Denver, and there's 2 different routes that go that way. So he's got 2 direct routes from Calgary to Denver. So let's map that out. So Calgary direct to Denver. There are 2 routes. Okay, so that's from here and here, right? He could go through Seattle. So first he's got 2 routes through Seattle, and then another 3 possibilities onto Denver. So Calgary, Seattle, Denver. He has 2 times 3 possible routes, which is 6 routes. Okay, now this situation, it's an either or. He can either fly direct or he can go through Seattle. So this would be an or option. So it would be the 2 plus the 6. So total routes is 8. Okay, so now remember, because he's going Calgary to Seattle, he could fly one way and then another. Because that has those joint points, we have to multiply. Whereas the direct routes, there's 2 possible routes, and that's it. Okay, use a little brain power. Arranging letters with restrictions when some letters are identical. So let's take a look at this. This is using our factorial. And we have identical letters. We have some different combinations. So we've got, in how many ways can all the letters in the word Toronto be arranged if A, there are no restrictions? So let's see what's identical. We have a T and a T, and then we have an O, an O, and an O. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 letters, and we have 2 T's, and we have 3 O's. So those are our identical letters. So we would go 7 factorial over 2 factorial times 3 factorial. And we would divide those, and we would get 420. Now we're going to add restrictions. So for this restriction, both the first and the last letters must be a T. So what that tells us is that we have, the first one's got to be a T, right? Then we have 5 letters in between, right? And then the last letter has to be a T. So this is what we're figuring out. Okay, we only have one option for both the start and the finish. In the middle, we have 5 letters. We still have those 3 O's. So for the middle, we'll have 5 factorial over 3 factorial, which will equal 20. Okay, but we take the T out of the consideration because we've used those as a restriction. Second says, or the third C here says vowels and consonants must alternate. So we're going to map that out because that's something different. So let's map that out. 7 letters, 1, 2, 3, 4, 5, 6. So I have 3 vowels and 4 consonants. So I got to start with my consonants, then my vowel, consonant, vowel, consonant, vowel, consonant. Now let's see what I have. Okay, my vowels, and I'm going to actually are all O's, right? My vowels are O's, so I have 1, 2, 3 vowels, and then my consonants are T, T, R, N. So let's see what options we have. For consonants, I have 4 options. Vowels, I have 1 option because they're all O's, right? Consonants, I have 3 vowels, 3 options. Vowels, I have one option because they're all O's. Consonants, I still have two options, vowels 1 and then consonants 1. Now, taking a look at what we're doing here, we've got a 4 times 3 times 2 times 1, which is 4 factorial. Now, the only thing is, with those consonants, I still have two identical terms, right? So that means I need to have a 2 factorial there because I have those two T's. Now the O's are all accounted for because they are what they are. So this is going to give me my answer, which is equal to 12. Okay. But I can't just have the 4 factorial because I have to remember that I have two T's. All right, the O's are all together. So let's think about that map. We have our O's together. They can move. But then I have a possible T, a possible T, a possible R, and a possible N. So within here, they're all O's. They're all the same. I have 5 entities because the O's move as a unit. So I have 5 things there, right? 5. However, let's think about this. With my entities, I still have those two identical T's. So those are going to be accounted for here with a 2 factorial. So even though I have 5 entities, 2 of them are still identical. And I have to take that into consideration, and that will give me 60 for my answer. Okay. Alrighty, let's move her up. Need to know. There are fewer permutations when the objects, when some of the objects in a set are identical. Okay. Number of permutations of n objects where A objects are identical, another B objects are identical, and C are identical is this formula. Okay. So this very important for identical objects. Okay. And what this does is this formula eliminates those repeated identical arrangements. It does that work for you. I mean, you can draw them all out if you want to, but I don't want to, right? When dealing with restrictions on permutations involving identical objects, calculate first the number of objects of arrangements with restrictions, treating identical objects as distinguishable objects. So calculate first those number of arrangements, okay? And then divide by the identical terms, okay? Pay really close attention to wording, okay? Phrases like at least, at most, exactly, they're restrictions, and you need to pay attention to restrictions, okay? Because they're going to affect the number of arrangements. The number of permutations that can be created from a set of n objects using R objects in each arrangement where repetition is allowed is n to the R. Okay, so that is the total. Okay, so now you have some practice. Hopefully this was fun. I enjoy it. I like these kinds